All right, welcome to the Explainer. Have you ever really thought about what a computer sees when it looks at a photo? Today, we're going to break down how AI figures out how to recognize something like a cat, starting with literally nothing but a grid of pixels. Let's dive in.
So let's start with the big question. When you show a picture to an AI and it immediately says, that's a cat, what's actually going on under the hood? It doesn't have eyes, it doesn't have a brain in the way we do. So what is it seeing that lets it make that call with so much confidence? Well, here's the thing. The way a computer learns to see using a technology called a convolutional neural network, or CNN, isn't actually that different from how we see. You don't just see cat in an instant. Your brain sees edges and curves first, then pieces those together into shapes like ears and eyes, and then, boom, you recognize the cat. A CNN does pretty much the exact same thing, just very deliberately, layer by layer.
So to really get this, we've got to start right where the computer starts with the raw data it gets from the image file.
Okay, this is the absolute key. A computer does not see a furry, cute animal. Not at all. It sees a massive grid of numbers. That's it. Each number just represents how bright a single pixel is in the picture.
And get this, for a color photo, it's even more abstract. It's not one grid of numbers, it's three of them, all stacked on top of each other. There's one grid for all the red light, one for all the green, and one for the blue. That's the entire universe the computer has to work with. Just three big spreadsheets of numbers.
Okay, so the computer has its numbers. How in the world does it get from that raw data to finding something meaningful? Let's look at the very first and maybe the most important step, finding the basic features, like simple edges and textures. Well, the magic tool for this is something called a filter. And you can just think of it as a tiny, highly specialized magnifying glass. Each filter has only one job in its life, to scan the image and look for one very specific, simple pattern, like a perfect vertical line, or a diagonal edge, or maybe a shift from a dark color to a light one. This process is called convolution. It sounds fancy, but really, the filter just slides over every single little patch of the image. And at each spot, it does a quick bit of math. If the pixels underneath it match the filter's pattern, it shouts out a high score. All of those high scores get recorded on a brand new map, which we call a feature map. Now here's where it gets really powerful. The network doesn't just use one of these filters. Oh no, it uses dozens, sometimes hundreds, all at once. So one filter creates a map that's basically a highlight reel of all the vertical lines. Another one maps out all the horizontal lines. A third might find a specific furry texture. All of a sudden, we've gone from a meaningless grid of pixels to a whole collection of maps that show us where the basic ingredients of the image are. All right, next up, the network does a little bit of housekeeping. It's a step called ReLU activation, and it follows a super simple rule. It just goes through all those numbers on our new feature maps, and if a number is negative, it just changes it to 0. It's a really clever way to clean things up, basically telling the network, hey, let's just ignore the weak signals and only pay attention to the features that were strongly detected. So now we have these cleaned up feature maps, but they're still huge and super detailed. The network kind of needs to zoom out and just get the gist. And it does this with a step called pooling. It basically shrinks each map down by looking at small neighborhoods of pixels and just keeping the most important piece of information. And this right here, this is the real genius of pooling. By summarizing the map, the network starts to care less about exactly where a feature was. It just cares that a feature, like a pointy ear shape, was found in a general area. This is what makes the AI so flexible. It's why it can recognize a cat, whether it's perfectly posed or curled up in a weird ball. Let's move on. We've found our basic building blocks, the edges, the curves, the textures. Now, how does the network put those little Lego bricks together to build something we would actually recognize, like an ear or a nose?
You're gonna love how simple this is. The network just does the same thing all over again. It takes those first feature maps, the ones showing simple edges, and it runs a new set of filters over them. But these new filters aren't looking for lines. They're looking for combinations of lines, like corners or circles. And that's how it starts to see shapes, like an eye or an ear. Then you do it again, and the next layer combines those shapes into bigger parts, like an entire face.
So at this point, the network has built up a really rich, layered understanding of what's in the image. It's identified all the important parts. Now for the moment of truth. How does it put it all together to make the final call? First, it takes all of those final, complex feature maps, the one for eye, the one for whisker, the one for fur, and it basically unrolls them all into one single super long list of numbers. This list is the ultimate summary of everything important the network found in the image.
Then, this massive list gets fed into what you can basically call the network's brain. And this is where the learning part really shines. Through tons of training, this part has learned to give each feature a score, or a weight, based on how important it is. It's learned that pointy ear and whiskers are huge clues for cat, so they get a high weight. And it's learned that a feature like a long snout is a really bad clue for cat, so that gets a very low weight.
Okay, we are at the finish line. All the evidence has been gathered, all the features have been weighed. Now it's time to tally up the scores and get the final answer.
The network crunches all those weighted features together and spits out a final raw score for each possible category it knows. So in this example, after adding everything up, the cat category gets a nice high score of 5.8, while the dog category only gets a 2.1.
But, these raw scores aren't very easy for us humans to understand. So for the very last step, these numbers are run through a function that just converts them into nice, clean percentages that all add up to 100%. And there you have it, a final, easy-to-read, confident prediction.
So just think about that journey for a second. The computer has gone from a completely meaningless grid of numbers all the way to a 97.5% confident prediction that this image is a cat. And it did it all by systematically building up simple features into more and more complex ideas.
And this whole thing leaves us with a pretty mind-blowing question, right? This same fundamental technique isn't just for finding cats on the internet. It's being used to analyze medical scans, to guide self-driving cars, to explore other planets. So, if a machine can learn to see a cat with this much detail, what are the real limits here? What else can it learn to recognize, to understand, and maybe even act on in the world all around us?